Let us talk about point forces. Point forces are one of the main topics in statics and dynamics and anything that has to do with structural mechanics, because point forces are the method used to find how much stress, strain, deformation is applied on a body or a system. So let's assume this irregular shape is anything. This is what it's supposed to be. Could be a bridge, could be a building, could be a car. And at this point, it's not telling us if it's um, the only thing we know is defined in two dimensions because there's an x and a y within this field. So the first thing we know is that this is defined in R2, and we have two dimensions. And the first thing we need to realize is that we can find the resultant force, the total force, by doing a summation of all the forces in the system. So we have, if I means a summation, means any force, because I could take, I don't know if you remember from calculus, when you see I could take um, values from, let's do this again. I could take values from 0, 1, 2, 3, etc. As many forces as we have. So this is simplified. So this means that R is equal to the summation of all the forces. We have 1, 2, 3, 4, 5, for example. So R is the summation of F1 plus F2 plus F3 plus everything else up until, say, F5, right? Or F15 or F150. How many forces we have? F is a force. In this case, we know that the force is defined as a vector. And we mentioned before, the vector needs two things, a direction and a magnitude. So a point where you start, a point where you finish, a magnitude, and a direction. The direction is related to the coordinate system. So many units on the x-axis, so many units on the y-axis. Okay, so the first thing is that when we need to know the total force on our system, hence the total amount of force applied on a bridge at peak hour, so we have a bridge that is designed to have, I don't know, say, and there are different types of bridges, so um, there are bridges that are structurally made um, from steel, bridges from wood, etc. Okay, so you can have different types of bridges. You can have a structure here holding part of the bridge, and a structure here holding part of the bridge. That really depends of what the design of the bridge is. Okay, so all these things have forces related to them. Okay, there's a force down because of the amount of amount of cars on the bridge. I don't know, that's gonna be tough to draw. Let's see, so single car, but could be hundreds of them, 1,000 of them, depending on how big the bridge is. Okay, so the total amount of force, depending on each car, depending on how many cars need to be correlated to the force that the bridge is going to see. Okay, so if there's 100 cars and there are 50 trucks, and we more or less have to calculate the total force of the bridge so that it can be designed for that amount of weight. Okay, so the total force, if R or capital R, is the summation of all the forces. Okay, but the next thing to know is that the forces have direction, and they are defined with respect to x and y. We've said that before too. All right, so in order to define the forces of x and y, we have to do a bunch of computations. They're pretty simple though. So a vector is defined with respect to x and y using sine and cosine. So fi, say f1, which is in this case, let's say f1, x and y, f1, this applies for every force, has an angle alpha with respect to x and an angle beta with respect to y. But for simplicity, we usually just use a trigonometry law where we say that f1 has this component in x and this component in y, in alpha. So this is going to be, this right here is going to be f1, the magnitude f1 equals, or f1 and x, I would say, the magnitude times cosine of alpha. And this is f1 and y is equal to the magnitude times sine alpha. So that's very simple. This is in degrees, okay, not in radians. This is in degrees. So if this is 30, this is going to be force, and I don't know, this is 10 newtons. This is going to be 10 times cosine of 30 degrees. And if y, the force in y, the component in y, is going to be 10 times sine of 30 degrees. Okay, so you use a calculator and get those values. If the system is moving, like an elevator, you're going to have some force is equals to mass times acceleration. Okay. Summation of forces is the summation of all the masses times the same acceleration or different accelerations, depending on what the system is. If it's a fluid, if it's multiple fluids, say oil and water moving in the ocean, you can have different accelerations, one for water, one for the oil. If it's an elevator, it's a single mass, and the gravity or the acceleration of the elevator itself. But if it's not moving, kind of we want to see what's the total force applied to a bridge after 100 cars drive on top. That's supposed to be as close to static as possible. We don't want the bridge being, jumping up and down and moving left and right. So in that case, we call that equilibrium. And it's basically meaning that the summation of all the forces are equal. So there's no acceleration. Okay, so we need to know that, for instance, in this case, this force could be the same enough to cancel out this force and that force. Or in this case, all these three forces or four forces need to be enough to cancel out this force. So even though this is having some internal stress because of all the force applied, it's not moving. It's internally deforming or stretching or bending or maybe some torsion applied to it, but this is not moving. This bridge is not moving from San Antonio to Austin. It's still in the same place where the bridge was located, but there's some internal forces that can actually, the force is too high, you can cause fracture or deformation that can damage it, and then maintenance has to be done. But the bridge is not going to be moving around like a car would move around when you put acceleration to it. So that's the second thing. The first thing is to compute in the total amount of force. The second thing is to know that in equilibrium, all the forces need to be equal to zero. So some are going to be positive and some of it going to be negative, so that when you do equilibrium, all of them are zero. That means that all the forces, F1 cosine of alpha, F2x, it's going to be F2 cosine of alpha, all the way to F n, if it's 100 of them, it's going to be Fn times cosine of alpha. Some of them are going to be negative, some of them are going to be positive, and they're going to be canceling out so that they end up being 0. And the same for if the force in y is just going to be sine of the angle and negative forces. How do you know if a force is positive or negative? With respect to your coordinate system. If it's towards the right hand side and up, that is going to be a positive force. If it's in, say just for x, if it's a negative or left hand side, it's going to be negative. It's towards the left hand side, and force in the vertical direction is negative if it goes down. So this vector, this force, is represented as the magnitude and direction. And as we said before, the direction is given by the unit vectors. The unit vectors are Ex and Ey. They're also called I and J, or K for 3D, and Ez for 3D. So the component of force in X, which is computed like this, and the unit vector in X, this is how you represent a vector in 3D. You cannot add up independent dimensions. You cannot add up the force, the component in X with the component in Y, but this is how you represent it. Another way of representing it is how we did it before. You just put F1 Ex, comma, F1 Ey, comma, if F1 Ez, and close it, just comma. Okay, but you sometimes could do plus, just because this is a common way of representing it. All right, we already know how to represent the vector in X and Y, and we know how to find the components. The magnitude is also very easy. We know this by now. It's the square root of each component. So it's the square root of this guy, the square root of that guy. So the X and Y, we're going to give you the components, and the magnitude is just the square root of that. And if you remember, this is the hypotenuse. So you just apply Pythagoras and find the magnitude. Okay. Similarly, in 3D, we have the case where the same thing happens. So we have our X, Y, and Z coordinate system. And then in this case, the origin is where all the vectors, or this only vector, Fi, F1 if you want, has the beginning, and the end is going to some point that is not given. If we wanted to do anything with this vector in terms of characterizing the vector, we would probably have to know what is the actual dimension. How many units in X, how many units in Y, how many units in Z. So as we said before, the vector is characterized with the components. And in 3 dimensions is exactly the same. You do cosine of the angle. So alpha, beta, and gamma are the Greek letters characterizing the angles typically. So if you want to know what is the component of the force with respect to X, it's just basically going to be cosine of alpha. With respect to Y is going to be beta, and with respect to Z is going to be F1 cosine of gamma. The cosine rule tells us that cosine squared of each angle, the summation of them is going to be equal to 1. So if you have 2 angles, you are asked to find the third, you only have to use your calculator and put this in. So you just do cosine squared, okay, of the angle. So you just type on your calculator that exact same thing. You usually will have to do cosine of the angle and the whole thing squared. Okay, that's how you do it. But this means it's cosine squared of the angle, because where you're doing cosine is not, this is not the same as cosine of the angle squared. That is not the same. This is not what we want. We want the cosine 2 times. Cosine of the angle times cosine of the angle. So what we want to have squared is the function cosine itself, not the angle. This is just a number. What we want to square is the whole function cosine. Okay, so this is okay. That is wrong. Okay, that is this. If you don't know how to do cosine square in your calculator, well, just do this, but you do have to learn how to do this because it's going to be easier. This will sometimes give you lose a lot of time just doing this in every time you want to do cosine squared. And the magnitude we already know for 3 dimensions is just each component squared.